All right, back from break. More chapter 17, more thermodynamics. This is, I'm guessing, looks pretty different from the first 16 chapters. And for some students, I'm guessing this is a welcome shift of emphasis too. And you know, whatever the situation, let's head forward. So the idea here for normalization would be to add together all of the individual numbers in each bin. And that would say that we want to integrate the function of v dv, add it together. It should give us the total number of molecules. So this is kind of what we talked about before. I'm thinking we don't have to, don't worry about any of this stuff. I'm going to go through it, I guess, fairly quickly. This is the function itself. The way that we would integrate that is to integrate it across all possible velocities. What that would become, if I take that function and plug it in, the m over 2 pi kt to the 3 halves come outside the integral. The energy factor and the 4 pi v squared dv factor, I'm going to leave those in. I know I could bring the 4 pi out, but we'll do that a little bit later. Now, for variable substitution, what I'm going to do is say that x, some variable I'm going to substitute in the integration, is the kinetic energy over kT. That's 1/2 mv squared over kT. U is a unitless variable proportional to the kinetic energy. And so with that substitution, v squared becomes 2kt over m times x. V becomes 2kt over m to the 1/2, x to the 1/2. dv, with this definition, if I take a derivative, that becomes 2kt over m to the 1/2, 1/2 x to the minus 1/2 dx. That all gets substituted back in. So this integral that we're calculating, these factors cancel out. I am left with my factor of 4 pi. There is a 1/2 and an x to the 1/2 inside here. I've got 2 pi over pi to the 3 halves. This is ex to the x to the half dx. And that works out, when we integrate that across all possible velocities, the factor we get from here cancels the remaining 2 over pi to the half, and we get n. So I cruised through that. If anybody wants to take a look at that and see how the normalization works, you're welcome to. Absolutely not required. So that's just something for a little bit of completeness. Sometimes when we go through these formulas, we don't have time to slow down and stop and see how they work. This seemed like maybe a time to do that. Again, no obligation for any of these. But the average velocity, which they wanted us to calculate, would come from taking 1 over n, that makes it an average, with the original probability function, but this time I'm going to put in a factor of v to each molecule, and then I'm going to add all the molecules together, all their speeds, and divide by n. And carrying out all of that integration, again, I'm not going to do all the details here. In fact, I'm just going to jump to the answer. When we carry out this integration, we end up with 8 over pi to the 1/2 times kt over m to the 1/2. That is the average velocity. Now, when I do the RMS velocity, that would be the average of v squared. So I have to put 2 factors of v into my integration and carry out the integration once again. With an extra factor of v, I'm going to have extra factors of the all the constants. I'm going to have extra factors of x. Instead of x to the 3 halves, I now have x squared. When I carry out this integration, I end up with 3 times kt over m. So there's the comparison. The average velocity is 8 pi square root times kt over m to the half. And the RMS velocity is 3 halves. And 3 halves, 3 kt over m, 3 is bigger than 8 over pi square root. Did we answer that question? I didn't. Okay, I realized I never solved the peak value. Let's see if they do that. Or let's see if I do that. I did! Okay, that's good. I write up these notes and then I forget what got included and what didn't. I'm always thinking what to include or what needs to get left out. So here's the function once again. And what we can do is to maximize a function, we want to take a derivative. So I'm just taking a derivative of that with respect to v, setting it equal to 0, and solving. And what I ended up with, again, I'm just going to jump to the results, is that the peak value squared is 2 kt over m. So there they are. The peak value, which is sometimes referred to as a mode in statistical terms, is the square root of 2, 1.41, times kt over m to the half. The mean value is 8 over pi square root, which is a little bigger, times kt over m to the half. And the RMS is the square root of 3, which is 1.73 something. Okay, what does that mean if I plug a bunch of numbers in? Well, we looked at nitrogen before and said its RMS value is 511. Well, the average value is 471. So depending on how much variation you allow when you're thinking about numbers, you could say, wow, those aren't very close, or you might be a little more relaxed and say, yeah, those are kind of close. You know, the RMS is not too different from the average value. The most likely value, the value where the probability peaks, is at 417 meters per second. Okay? So, that was a good set of calculations that we carried out. We showed using maybe more than a little calculus. We were able to come up with formulas for the mode, mean, and RMS velocities. This is something that's useful. Again, let me restate that you're not responsible for doing this sort of stuff. This was just, you know, kind of a high-level example of going in and using calculus. If you're inspired by this, maybe you want to change your major to physics or something. But in any case, I just wanted to get to the point where we could take a look at the comparisons with the different speeds. How much variation do we see between the different ways that we do averaging? All right, for the rest of the chapter, what we want to take a look at are different phases of different materials. And again, water is an easy one to come back and look at. So what we're looking at right now are phase diagrams. And the phase diagrams typically are looked at in terms of pressure and temperature. So I can take a container of water. So ideally what I would want is a flexible container. And so a flexible container would mean that, you know, I can adjust the volume. So what I can do is, if I want to, is I can adjust the volume, and I can also, in some sense, control pressure by reducing the volume or increasing the volume. So I'm going to have control over volume, and then I also need control over temperature. Now to have control over temperature, that just means I have to be able to take my container and place it in a warmer environment or place it in a colder environment. So that's how we control temperature. If I want the molecules to move faster, I put them in contact with other molecules that are already going faster. And just from random interactions between the molecules, we will have thermal energy that transfers from the faster moving molecules to the slower moving molecules. If I want my molecules to slow down, if I want the temperature to drop, I put my molecules in contact with slower moving molecules. And again, just through random collisions and interactions between those molecules, energy will end up transferring. We call it energy transferring. It's really more molecular motion ends up transferring into regions of less molecular motion through collisions, and it averages out. So that's what, when someone says, let's heat this up, that's what they really mean. Let's put it in a region where there's faster moving molecules, and then some of that molecular motion will transfer over. Or let's cool this down. What they really mean is let's put it in an environment where the molecules are moving slower, okay? And allow some of that molecular motion to transfer out. Anyway, here is the phase diagram for water. And let's walk around this a bit. These phase diagrams, I don't know what your experience has been with them. I'm guessing most of you have probably taken physical science classes where you looked at these. I can spend hours getting kind of caught up in some of these and thinking about what they're really telling me. So again, pressures on the vertical axis, temperatures on the horizontal. Let's try a few walk-arounds and see what would happen. First of all, let's start, it's water. Remember, it's a container with water in it. So one thing I want to do is say, let's start with 1 atmosphere pressure. So if we have 1 atmosphere pressure, and we're going to maintain 1 atmosphere pressure throughout, let's start at a low temperature. Now, something I should point to is notice that the vertical scales, this is 1 atmosphere, this is 218 atmospheres, this is 6,000ths of an atmosphere. They're not to scale. So what they're trying to do is show, the scales are probably logarithmic, but in any case, they're just trying to show certain features as to how this works. Again, the temperature scale is the same thing. This is 0, that's 100. This is 374 Celsius. So let's go to a low temperature. Maybe this is minus 40 or 50 or 60. Anyway, for the water, at these low temperatures, at 1 atmosphere pressure, it's a solid. It's a block of ice. And then what happens as we increase the temperature? So we're going to put it in a warmer environment. We're going to let the temperature of the water molecules come up and get more and more vibrational energy of the nuclei vibrating back and forth, oscillating back and forth within the surrounding electrons. At some point, what happens is the molecules begin to go liquid. So once we get to a high enough kinetic temperature, there's enough kinetic energy in those molecules. Molecules now can separate from the ice, from the rigid crystal structure. Now, that happens at the red line here. This represents a phase transition, and this is the boundary between solid liquid. Now, when we get to this point, and I keep adding energy, the temperature does not immediately go up. Here, where I was adding thermal energy, I could see a temperature increase, but that's a phase transition, and the phase transition itself requires energy. So we refer to this as a latent heat, and things are going to stall out here for a while as the molecules, one by one, separate themselves from the crystal structure, so they're transitioning from a solid to a liquid. And again, that's going to take a good amount of energy to create that effect. So I'm adding energy. It's a solid, but it's at a higher and higher temperature, and then the phase transition, things stall out right there at that red boundary as I keep adding energy. Once all of the molecules have gone liquid, and I continue to add energy, then the liquid, I start to increase temperature once again. And so this is now the water is a liquid sample, and the temperature within the water is going up, 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 up. And then what happens when the water gets to 100 Celsius? Now the individual water molecules, not just at the surface, but throughout the sample, now have enough energy that they can go vapor. So, and again, it's not just individual molecules at the surface of the water that are leaving, it's that the water molecules throughout begin to form little bubbles of vapor. And the bubbles of vapor are at 1 atmosphere pressure. And since the bubbles of vapor are at 1 atmosphere pressure, they're able to hold their own. They're able to sustain. And so what will happen is throughout the sample of water, we'll be seeing a vaporization process happen. And again, the temperature stalls. So we're dumping a bunch of energy in. Vaporization requires a lot more energy input than going liquid. Going vapor, we're going to have to put a lot of energy in here. And then once every last molecule has gone vapor, then as we add more energy, the temperature will go back up. So we went from solid to liquid. So we went through a temperature increase of the solid and more vibrational motion. So we're, as the temperature goes up and we go through these different phases, that means that the molecules have more energy. And initially that's vibrational energy of the nuclei in the solid. And then we make the transition. Now we continue to have vibrational energy, but now in addition we have translational and rotational energy of the individual water molecules in the liquid. And then once we make the transition to vapor, we have translational energy and rotational energy. We're going to find out there's not actually as much vibrational energy for certain reasons until we get to much higher temperatures once we're in the vapor form. But in any way, that's an interesting walk to do. Now, there's what's called the triple point. And the triple point says that there is a particular pressure and temperature at which we will have a combination of vapor, solid, and liquid, which are all in equilibrium with each other. And that's referred to as the triple point. So there's that one particular temperature. It turns out that it's just above, the triple point temperature is just a little bit above 0. It's at 0.01 something. I should have looked that number up. That's only 1 sig fig. We need more than 1 significant fig. It's a temperature scale, so maybe we're okay. We're down to the hundredths of degrees Celsius. Now on the pressure side, I did look this up. This kind of stuff drives me crazy. What does 0.006 mean? We can do better. We got to have more than 1 significant figure. So I looked that up. It turns out that the triple point of water occurs at 0.00, I want 3 sig figs, so 603 atmospheres. Now if I convert that into pascals, which would be standard units for this, the standard units would say that it converts into 612 pascals. So atmospheric pressure would be 101,300 pascals. But now we've dropped the pressure. That's a really low pressure. So the pressure here is at 612, I believe, pascals at the triple point. So what would happen here then if I drop below the triple point pressure? Let's go down to 500 pascals. So again, we can start at this, it's really, really low pressure. And we're going to start at, maybe minus 40 Celsius. And it's ice. So it is solid ice. The pressure is really low this time. And what happens is we get to this transition. There's a latent heat. But notice this transition is from solid to vapor. So as the kinetic energy goes up in those individual nuclei, and the molecules begin to separate, once they have enough kinetic energy, they completely separate. They don't go into liquid, they go into vapor. We're going to call this region vapor. And then as the temperature goes up, it just continues to be vapor at higher and higher temperatures. So the higher and higher temperatures of the vapor suggest more and more translational kinetic energy, more and more rotational kinetic energy, and at some point, more and more vibrational kinetic energy. Now, what's interesting here, I think I may have mentioned this already, Mars, we've got all these rovers on Mars going around searching for signs of water, and they found it. So they found that if you dig under the surface, you find little crystals of ice. So you do find solid water on Mars. Now when they dig down below the surface and they identify these crystals of ice, and then they take pictures of it, the ice is not converting to liquid. The ice is going directly into vapor. Now, what does that say? The ice is undergoing what's called sublimation. So I believe that, well, I had thought that the pressure on Mars, it's really low, was below the triple point of water. But it turns out that the pressure on the surface of Mars is just a little above the triple point pressure. So it does, and it's just above this value. It's like 650 pascals. And so on Mars, you have this small region here between these temperatures where water could exist as a liquid, possibly. I have to go back and double check all these numbers. But it does sound like there is this small temperature range in and around 0 Celsius, or just above 0 Celsius, where you could have some liquid water form. But it would be over a very limited temperature. There'd be a very small difference between liquefying the water and then vaporizing the water. In any case, that's kind of interesting that on Mars you're dealing with pressures that are right around the triple point for water. Whereas on Earth, there's a wide range of temperatures that allow water to be in the liquid state, and that's what we find is water is ubiquitous on the planet. Liquid water is ubiquitous. Now, what would happen if we went to a high pressure? What if we went up above this, what's called the critical pressure? When we went at 1 atmosphere and we walked over and we got to a certain temperature, there was a distinct phase transition where liquid turned into vapor. And we know the difference between liquid water and water vapor. If you go above 218 atmospheres, if we're coming in at 220 or 230 or 300 or something, we do have a transition from solid into what looks like a liquid. But when we follow that liquid water to higher and higher temperatures, we find out there is no distinct transition to vapor. Instead, what looks like a liquid at higher and higher temperatures becomes less and less dense until at some point you go, you know, it really looks more like a vapor than it does a liquid. But there's no transition. So the phase, this is kind of a interesting, remarkable property that beyond the critical point for materials, liquids and vapors there's no difference. Okay, there's no transition that takes place. Now, different textbooks categorize this differently. Our textbook says that as long as the temperatures and pressures are within the critical values, we're going to refer to this region as vapor. We're going to refer to this region as liquid, but anything out here is referred to as a gas. And I don't necessarily care for, because if you transition to here, you would definitely look at that and say, it looks like a liquid. Okay. Now I noticed that the chemistry textbooks that we use here at Laney, they categorize this differently. I think, if I remember right, they call this gas, and they call this supercritical fluid. Ooh, supercritical fluid. Anyway, I just want to call this liquid, and that the liquid gradually transitions to vapor without a distinct boundary. Okay, is to me more intuitive as to what this would look like. But again, these phase diagrams, they're kind of interesting. Let's try just a couple more examples here. What would happen if, instead of fixing the pressure, what if we had a fixed temperature and then gradually increased the pressure? So, let's try this. Let's say this is 20 Celsius. So if that represents 20 Celsius, let's start with really, really, really low pressure. So let's go down to just a few hundred pascals. So we'll go down to a few hundred pascals, and we'll start off at this temperature, and at that point, the water would be vapor. At those very, very low pressures, the molecules are going to be a vapor. What happens for water then, as the pressure increases, at some point we make the transition from vapor to liquid. So what that's indicating is, going from vapor to liquid, does that require a temperature change? And it doesn't. We could go from vapor to liquid just by changing the pressure. So again, if we start out with really low pressure, it's going to be in vapor form, and as we compress the sample, at some point just using pressure and allowing the sample to maintain a constant temperature is going to take us up through this liquid region. So we'll go from vapor to liquid just using pressure. We could reverse that. We could start off at atmospheric pressure, and as we drop this is what we mentioned before. If we earlier back in the fluids chapter, there was a point in the fluids chapter where they said something like, we're always battling against atmospheric pressure or something. I know I'm exaggerating, but they said our cellular structures have learned to compensate for this high pressure, and actually we need this pressure. If we drop down below a few hundred, 600 pascals, water doesn't exist as a liquid. So that would go back to vapor if the pressure got to be really low. All right, we could also do this. We could go to a low temperature, maybe minus 20 or minus 40 Celsius, do the same pressure increase. Notice at low pressure, we're always starting as a vapor. And then as the temperature goes up, at some point we will transition. As we compress the vapor, it'll make a phase transition, but if it's a low temperature, it transitions to a solid. Okay, so that would be from vapor to solid. If we did it the other way around, let's take a block of ice. So if I take a block of ice at 1 atmosphere pressure, and then I begin to remove the pressure, I don't lower the temperature or raise the temperature. I keep the temperature fixed at, let's say, minus 20 Celsius. So I'm keeping the temperature fixed, but I'm lowering the pressure. At some point, as I lower the pressure, that block of ice will sublimate. It will go into vapor. Okay, so it's kind of fun to play around with all these. You fix one of the pressures or you fix one of the temperatures, and you walk back and forth and see what happens as you change the other variable. So this is the phase diagram for water. The phase diagram for carbon dioxide, just for comparison, the triple point for carbon dioxide is at 5.11 atmospheres. Now, Earth pressures are way down here at 1 atmosphere, and so at 1 atmosphere, the carbon dioxide can exist as a solid or a vapor, but it can't exist as a liquid. If I want to see a sample of carbon dioxide, liquid carbon dioxide, I have to create an environment where the pressure is larger than 511,000 pascals. I got to go up to 5.11 atmospheres, and if I do that, then carbon dioxide can be a liquid at that point. I'm sure you can go online and look up liquid carbon dioxide and see pictures of what liquid carbon dioxide looks like. We'd have to go to a much higher pressure. And we would have to do that's at a low temperature too. So if we were to do this at room temperature, we would have to take the carbon dioxide up to 56 atmospheres of pressure to have liquid carbon dioxide at room temperatures at 20 Celsius. So again, same features, critical points, triple points, kind of fun to play around with these, but they can be tricky. Now, one thing I wanted to point out too is that these phase diagrams that we've looked at for carbon dioxide and for water, they're only showing pressure and temperature. We mentioned before we started that once I know the pressure and the temperature, that's enough information, and I know that the number of molecules in my sample, that's enough to determine the volume. So what we can also do is create these three-dimensional phase surfaces where this axis is pressure, this axis is temperature, but now we've done is we've projected out and shown what the volume looks like at each one of those pressures and temperatures. So in some sense, the same information is here, except we don't know what the volumes are. There's enough information here to work from that we could bring out three-dimensionally the volume. And that's kind of interesting because then you can see some of the shapes of how, just how much expansion are we going to get when we go from a liquid or a solid into a vapor. So when we go into the vapor, we see that the volume goes way up when we make that transition into vapor. And as we go to higher and higher temperatures, we can see that the volume of the vapor is going to go up as we go up to higher and higher temperatures. So the vapor volume is more variable. The liquids and the solid states their volumes don't vary so much depending on what the temperature is. So this is another one that you can kind of stare at, maybe in your physical science classes, maybe in high school or something. Maybe they had some of these lying around. I think I remember in my own high school, we had some of these surfaces lying around like in the chemistry room. And they were just fun to stare at and kind of think about how pressure, volume, and temperature were all related. Now, here's kind of a picture showing what the this container might look like. Now, I had suggested we need a flexible container, so I'm going to go back and say, I wish this were flexible so that the volume could adjust. But in any case, we've got a certain pressure inside here. Here's the liquid portion. This is right at the boundaries between liquid and vapor, and so we've got both phases present at the same time. The slide here is actually talking about evaporation. So if we took some water, for evaporation, I think I would just want to cut off this lid and let the water molecules separate. At that boundary temperature, you're at a point where there's enough kinetic energy that some of the molecules go vapor, but then some of those gas molecules lose kinetic energy on collisions or something, and then the next time they hit the water, they stick because of attractive forces with the other water molecules. So you've reached an equilibrium where the number of molecules going from liquid to vapor match the number going from vapor back to liquid. And so that represents an equilibrium state, and we could go back to the phase diagrams and find a point that represents that. So again, they're talking a bit about this equilibrium back and forth between these two phases. Now here is a table of what's called saturated vapor pressure. So let's go back and look at that container again. The saturated vapor pressure would mean this. Let's take all the air out of the container and then close this off and then ask how many of the water molecules go into vapor form and how much pressure is there. How much pressure is there among the water vapor molecules, because that's going to determine what the pressure is inside. Whatever the pressure is being generated by these gas molecules, that's going to match the pressure at the surface of the water, and we're going to treat it as if that's roughly uniform. Now, in this table, they list this in terms of millimeters of mercury, and they also list it as pascals. Again, millimeters of mercury are kind of, I think that's kind of a crazy set of units to work in terms of. So I'm going to cross all these out. I'm going to pretend those aren't there. And instead, I just want to talk about the saturated vapor pressure in terms of pascals. At 0 Celsius, the vapor pressure due to those water molecules inside there, it would only be a pressure of 611 pascals. Okay, very close to the triple point. But then as the temperature goes up, we can see that the pressure goes up slowly at first, and then it begins to climb very rapidly. Now, by the time we have heated that to 100 Celsius, what we're finding is the vapor pressure, due to the water molecules by themselves, is matching 1 atmosphere. Okay, and once you reach 1 atmosphere of pressure, so we're going to raise the temperature on these, we're going to get more and more of these water molecules going into vapor, and that means the pressure will go up. We got more water molecules and they're moving faster, the pressure increases. At some point, at 100 Celsius, the water vapor molecules that form are not just coming off the surface anymore, they're starting to form within the liquid itself, and that says that the vaporization process for the sample has started. And so the vapor pressure that we have at 100 Celsius matches atmospheric pressure, and something will start to boil. Now, what if we keep the pressure higher? You know, these water molecules are reaching 1 atmosphere and they start to form bubbles. We take the lid off so that it's out, you know, the pressure is 1 atmosphere. Or we make it flexible so that there's 1 atmosphere pressure. What happens if we increase the pressure? Well, increasing the pressure can force some of those water molecules back into the liquid state. So, and this is what we do with a pressure cooker. So with a pressure cooker, let's say, you know, the food can only hit 100, if I'm boiling water and cooking something, the highest temperature that water can get to is 100 Celsius. So that limits how fast I can cook that food. You know, maybe I got some beans that I want to boil. I want to, you know, make a bunch of beans, and I put them in this water and I boil it. And it's taking a long time, and one of the reasons is the temperature of the boiling water can only reach 100 Celsius. Now what we can do is we can put it in a pressure cooker. And if we put it in a pressure cooker, what that means is that we can now go to higher temperatures. The pressure inside the pressure cooker is going to go up to, let's say, 2 atmospheres. Well, what happens if the pressure cooker is able to maintain 2 atmospheres of pressure? At 2 atmospheres of pressure, we can keep the water liquid all the way up to 120 Celsius. So it's a higher temperature, the food will cook faster. If my pressure cooker goes up to 476,000 pascals, you know, somewhere around 4.7 atmospheres, if I go up to 4.75 atmospheres, I can cook the food at 150 Celsius, and that will make it cook considerably faster. When I was a kid growing up, and I was cooking, which basically meant boiling some water and maybe putting an egg in there or something, you know, cooking an egg. My dad would always, I would turn the range top up, you know, just a high value to get the water to boil as fast as I could. And my dad would always remind me, he goes, once it's boiling, that's as hot as it is. He goes, you can turn down the range top. As long as you turn it up high enough to maintain a boil, that'll be at 100 Celsius. And the food's not going to cook any hotter by turning it up higher. So that's always something to remember. Now, earlier on, we had talked about what the atmosphere consists of, you know, what percentage of what molecules are in the air. And what we're showing here with this saturated vapor pressure is if I'm at a temperature of 30 Celsius, which is a, you know, it's a nice warm day, what would that be, like in the 80s or something? If the water, if I have plenty of water around and all the water is evaporating into the air, so that we actually saturate the air, we go to 100% relative humidity, we could have as much as 4,240 pascals of pressure due to those water molecules. Well, at 4,000 pascals, that means 4% of the pressure is coming from the water molecules, and that would mean 4% of the molecules in the air are water. So if it's 100% humidity, though the atmosphere is saturated with water at a temperature of 30 degrees, then that would give us the water molecules making up 4% of our atmosphere. So that's in a case of it's really humid versus really dry. We could also have the atmosphere at that temperature where there are so few water molecules around, there's basically zero water molecules in the air. So it depends on availability of water molecules to help determine what the humidity will be, what will be the partial pressure of the water molecules. Now here's an example of boiling. We've mentioned a couple times that once we hit that transition, that phase transition, individual bubbles of water vapor now are at 1 atmosphere. Once we hit 100 Celsius, the little bubbles that form are at 1 atmosphere, and since the surrounding pressure is 1 atmosphere, the bubbles are sustainable. And so the phase transition is taking place with that. Now we can calculate something called relative humidity. Relative humidity is defined as the pressure being generated by the water molecules in the air. We call that a partial pressure. So if I have a mixture of gases, each gas is contributing to the pressure, and each compound contributes to the pressure based not on the molar mass, but just on how many molecules there are. Because each compound has the same translational kinetic energy on average, they contribute to the pressure based on the number. So I can look up what is the partial pressure of H2O, that'll tell me how many water molecules are water, and then I can compare that with the saturated pressure. So this would be the actual pressure of the water molecules versus saturated. Now if if the number of water molecules in the air are equal that saturated water pressure that we talked about from the chart, then the relative humidity would be 100%. But typically we're well below that 100% number unless, the humidity is really high. So here's a problem. It says that on a particular hot day, it's a nice warm day, the temperature is 30 Celsius, and the partial pressure, the pressure due to the water molecules in the air, is at what? 21 millimeters of mercury? No, I can't use those units. Have to cross this out and quickly convert. I can't look at those units. What is the relative humidity? So let's take a look at this example. So the pressure that they've given us, it's not 21 torr, it's 4,240 newtons per meter. Those are pascals. Okay, I got rid of the millimeters of mercury. Let's see, so this would, this would be saturated. This is the number that they gave us. So the number they gave us, which was, I guess I have to say it, 21 torr, I quickly converted into newtons per square meter. And I did that by saying, look, 1 atmosphere is 760 millimeters of mercury, there I said it, and 760 torr, that's the same thing, that's 101,300 pascals. So that says every millimeter of mercury is 133 pascals. So there's your conversion. Next time you're at the doctor and they say that your blood pressure is 110/60, say, what units are you using? Oh no, please don't give me millimeters of mercury, that's archaic. Please, let's do the blood pressure in pascals. Okay, try it and see how that goes. Anyway, so it says that the number they gave us in the units which will not be spoken are 2,800 newtons per meter. And so the relative humidity is, this is the measured pressure, and this would be the pressure if we were at saturated water vapor. If we reached equilibrium of how many water molecules will make up how much pressure will be coming from the water molecules. So this is saying we're at 66% of saturated water pressure, so we report that as a relative humidity. Now that's going to depend on what temperature we're at, so we got to think in terms of temperature. So here, such a pretty picture. Those mountains are just beautiful. And what's happened here is fog, and it's not like here in the Bay Area, we're not familiar with fog. We know what fog is like. So what happens is this: during the daytime, the temperatures go up, water is evaporating, we're getting a lot of water vapor in the air, and so we've got a certain amount of water molecules there, and then the temperature drops. And at the lower temperature, that's too many water molecules, right? The equilibrium shifts at the lower temperature so that fewer and fewer water molecules can actually remain in the vapor state. Now what happens with those molecules in the air is they slow down, and they're still colliding with other water molecules, but at slower speeds, when one water molecule runs into another water molecule, the potential energies take over. The attractive force between the water molecules takes over, and the water molecules stick. So, and then we start to get clumps of water molecules. We get what we call water droplets in the air. And that's what fog is, and that's what clouds are. Fog and clouds are made of what we call water droplets. The water molecules are no longer moving around individually. Now they clump together. And when they clump together and form water droplets, light can be scattered by those water droplets. Individual water molecules do not scatter light very well. They're basically invisible. You know, light easily passes through an atmosphere that's got a lot of water molecules. Having a bunch of individual water molecules, the light can easily pass through. But when water droplets form, then you get, it's no longer transparent. The light comes through, and it's very likely the light will scatter off those water droplets, and so it's clouds or it's fog that the water becomes. And we call this the dew point. We say that, okay, it's the end of the day, a certain number of water molecules have gone into the atmosphere. We can count how many water molecules are there, and then we can say, okay, with this many water molecules, there is a temperature that if we drop below that temperature, water droplets are going to start forming, and we call that the dew point. That's the temperature at which, based on the number of water molecules in the air, we will get condensation. And so if it drops below that temperature during, the nighttime, then you wake up in the morning and there is dew all over everything. And it could be foggy outside. So you get the water condensing into droplets. It sticks to the ground, it sticks to the plants, it sticks to the buildings. Everything's kind of damp in the morning because the temperature dropped below the dew point. Okay, so in the winter, when you're heating air inside, you're taking cold air and you're heating it. But remember, as temperatures go up, the relative humidity will drop off. As temperatures go up, we're expecting more and more water molecules to be present in that air. But if you're just heating up the air, you're not adding water to it. So if the air becomes really dry when you're heating that in the winter, people get vaporizers, or they just boil water. You put some water on the stovetop, you turn it on, you put some more water molecules in the air, and it doesn't feel so dry anymore. Okay, I added a couple of topics at the end here. I think we have time to fit these in. You're not responsible for these. I hope that sometimes if you're not responsible for stuff, it actually makes it kind of interesting to look through. So we have been looking at gases using the ideal gas law. You may have heard of different formulas that are more accurate in describing the properties of gas molecules. One of these equations is called the van der Waals equation of state. And what the van der Waals equation of state is trying to take into account is that the molecules themselves take up a certain amount of space. So there's kind of an excluded volume that the gas molecules cannot access. You know, they can't access the volume being taken up by all of the other molecules. And so the van der Waals tries to take that into account. And this is what it looks like. So notice what they've done is they took pressure and they took volume and they complicated them. Now, the A and B are intended to be constants that are measured experimentally due to a gas. And so what happens here is this. If we take, this is not a PT diagram, this is a PV diagram. Now, if we take the ideal gas law and we say, what would an isotherm look like given the ideal gas law? If T is constant, then the P versus T graph looks like a hyperbola. So this is a constant temperature. As the sample volume goes increasing, then the pressure drops off and vice versa. Now what happens is, this is at some temperature, you know, maybe this is 300 and this is 200 or 100. By the time we start to approach lower and lower temperatures, those hyperbola are not what we see experimentally. And what we're saying is we're starting to see the effects of not only the excluded volume from the molecules themselves, we're starting to see the effects of attractive forces between the molecules. Now, we said that attractive forces between the molecules, we're going to think of those in terms of potential energies. And these potential energies are due to these attractive forces. So this is where we start to go into a phase transition into something that would be liquid instead of vapor. And that is one of the things that the van der Waals equations transition away from these nice hyperbolic isotherms and then accurately represent these others. So that's the reason it's created. So the van der Waals equation of state will actually give us, potentially can give us a better representation of how the gas is behaving at temperatures and pressures where it's near a transition point. Okay, anyway, just something to be aware of. The other question that comes up is how far do gas molecules travel within the air? That's kind of interesting. We talk about these collisions, but on average, how far is it between when a molecule interacts, it bounces off another molecule, and we have what's called the average path, or the mean free path. On average, how far can a water molecule go without being affected by its neighbors? This is not derived, this is just a formula they gave us showing the mean free path. And then the diagram here is kind of indicating how that was derived. The idea is to take one molecule, assign it a certain radius or a certain diameter, and then have it go through a region and ask how many molecules are going to be within that region where it might have a collision. So again, don't worry about the details of this. This is kind of an interesting example though. It's taking the air molecules at STP. Oh, but STP is so cold. So anyway, it's saying what would be the mean free path of an air molecule at this temperature. Now it says, 99% of the air molecules are O2 and N2. They're about the same size. It says they're about 300 picometers. So let's take a quick look. I am curious, how far do they travel? So this is the number of molecules per volume. I need to know how many air molecules there are per volume. So I can calculate that from the ideal gas formula as pressure. That's the pressure of the atmosphere, Boltzmann's constant, and absolute temperature. And it says that at 1 atmosphere pressure and kind of room temperature, there are 2.5 times 10 to the 25 molecules per cubic meter. So that's good to know how many molecules we have per cubic meter. And then the radius of these molecules, we're going to say, is about 150 picometers. I just want to double check. This was a yeah, it was a diameter. So they gave us a diameter of 300, and I reduced that to a radius of 150 picometers. And then I plugged the numbers in. I plugged all the numbers into this formula, and I got an average distance of 100 nanometers. That would be 100,000 picometers. So 100,000 picometers that the molecules travel on average before they collide with another molecule. Now, how many diameters would that be? And it works out, that's about 300 molecular diameters. So that's saying I've got a nitrogen here, and it travels a distance of about 300 diameters until it runs into another nitrogen, or it runs into an oxygen. Okay, so I just thought that's an interesting number to think about for the air molecules. We've already looked at the air molecules and shown that they're moving at like 500 meters a second. So 500 meters a second, these collisions are going to happen pretty regularly. They're going to be very, very short. I should have calculated the time spacing between that if they're traveling at 500 meters per second. Anyway, it's about 300 diameters between one collision and the next. And then there, just to wrap stuff up, there are these nice pictures of diffusion. And so the idea of diffusion is that as these molecules bounce around and travel these different distances, they're gradually going to randomly spread out through the sample, and that process is called diffusion. Okay, and they've got a table of numbers here about how fast diffusion takes place with different types of molecules. Okay, and that wraps up chapter 18. So if you guys have any questions on any of this stuff, let me know. Stop by office hours, and we will get those questions looked at.